So here we have this four-dimensional function here. F of x, y, z equals 3x squared minus y squared minus 2z squared. And we're asked to prove continuity at x naught. This point x naught here equals 0, 1, 0. And we're going to use an epsilon delta argument to do this. Cauchy-Schwarz, right? I'm going to iterate what that is here. That's just, so f will be continuous. F is continuous at x naught if for all epsilon greater than 0, there exists a delta greater than 0, such that if f of x minus f of x naught, if that's less than epsilon, then this distance, the distance between the two initial points there, or the distance between the one initial point and the current point, x minus x naught, if then that will be less than delta. So what does this mean here? Less than delta. So what this means basically is if we take the distance between f of x and f of x naught here, if we can set that to be arbitrarily small for some for some number, it's greater than 0, the distance, but it's arbitrarily small. If that's true, and then we also have that the distance between the points is small, this right here, then we can say that it's continuous. This is the Cauchy-Schwarz criterion for continuity at a point. And notationally speaking, I'm just writing this f of x, y, z as a vector x right here. So just for the sake of not having to write so much. So this is x, y, z here. So that there's no confusion. That's right there. It's just the vector x, y, z. All right. So we're going to do this for this equation here. So let's start here. So we're going to want to simplify this right here and get it to look like this. So we're going to assume that epsilon is greater than 0 and that this f of x minus f of x naught is less than epsilon. So we have then that f of x minus f of x naught, we have that is less than epsilon. And I'm just going to simplify this. I'm going to expand this out. So that's equal to, what's our equation here? That's equal to 3x squared, absolute value of 3x squared minus y squared minus 2z squared. And then we're going to subtract the f of x naught here. We're going to plug in that point. I'm not going to fully simplify it though, and you'll see why in a little bit here. So that's less than, oh, that's equal to, so 3 times 0 minus a negative is a positive, so plus 1 squared. I'll just write plus 1 minus 2 times 0. I guess plus 2 times 0 because minus a negative. All right, we have that then. Let's rewrite this. Let's kind of pair these up with their corresponding x, y, and z values here. So we can group the 3x minus 3 times 0 together, and we're just going to get 3x squared right here. And we're going to group the y and the 1 together, so we have minus y squared plus 1 right there. And then the two z squared and the 0 is going to be grouped together, so we have minus 2z squared plus 0. I'm just leave it like that. Okay. So let's make sure we're doing this correctly here. All right. So the triangle inequality states that if you have an absolute value of this sum here, a plus b, that's less than or equal to the absolute value of the individual parts, a plus b. So we're going to apply that here to get this is all less than or equal to 3 times the absolute value of x squared. And I realize I don't need to put that absolute value there, but I'm just going to so we can stay organized here. And that'll be plus absolute value of y squared, absolute value of y squared minus 1. You see how I just switched the signs around there. And then that's going to also be this 2z squared right here. And the reason you'll notice I switched that sign there on the z term, but that's just because if this is less than or equal to that minus 2z squared, it's certainly going to be less than or equal to it plus 2z squared. So we need this to hold for another inequality we're going to use here. So there's another inequality we can use. It's called Schwarz's inequality. It states that if we have two vectors u and v, and we take their dot product, and they take the absolute value of that, then that's going to be less than or equal to the individual um, vector norm u times v, like that. So what we can use this for is we can um, we can say that this whole thing right here is notice that this is just the vector 3, 1, 2 dotted with the vector x squared, y squared minus 1, z squared, right? That's all that this is right there. Another way to think about this is just 3, 1, 2, that vector dotted with this this vector x minus x naught right there. All right, so it's starting to come together here. So by the Schwarz's inequality, then this is going to be less than or equal to, um, we can take we can simplify these parts and just write them as we had down here to get x minus x naught. And then that's going to be less than, or this whole thing is going to be less than or equal to that times the norm of this vector right here, right? From Schwarz's inequality. So that's the norm of that vector is just going to be the square root of the sum of the squares of the individual elements. So that's just going to be the square root of 3 squared plus 1 squared plus 2 squared, which is it's just the square root of 12, right? And we know all that. We know all that from this part being less than epsilon. This is going to be less than epsilon right here. So what do we do from here? So we have that that's less than epsilon. So we say that we let epsilon equal some product of something times delta, some multiple of delta. So we pick it in such a way that this square root of 12 is going to cancel out. So we let epsilon equal delta times the square root of 12. So we have that f of x minus f of x naught. We have that that's less than delta. And then we also have that x minus x naught root 12 is less than is less than epsilon from these steps we performed up here. And for epsilon equals delta times root 12, the root 12s will cancel there, and we can see that this difference here, this distance between x and x naught, is less than delta, which is what we were trying to prove there. So let's state everything and sum it all up here to finish this off. Thus, for f of x minus f of x naught less than epsilon, we have that x minus x naught is less than delta. So we have continuity. Have continuity at x naught. I guess that's the real end of the proof right there.